Right now, the universe is being pulled apart, not by explosions or collisions, but by space itself stretching in every direction. Between galaxies, between stars, the distance is growing, faster and faster with every passing moment. Astronomers call the force behind this expansion dark energy, and it dominates reality, making up nearly 70% of everything that exists. We live in a cosmic ocean where small islands of matter drift farther apart every second, never to reconnect. In this journey, we'll travel through enormous voids that should not exist, explore why the universe appears strangely silent of other civilizations, and glimpse what may await when emptiness finally takes over. If you're ready to confront how unsettling nothingness can truly be, hit the like button and let's begin. Look around you for a moment. Everything that feels solid and real, the ground beneath your feet, the air moving through your lungs, the cities we build, the mountains rising from continents, even the stars scattered across the night sky, is made of matter. For most of human history, it was natural to assume that the universe must be filled with this substance. After all, every direction we looked seemed crowded with things. But the deeper we began to explore space, the more unsettling the truth became. The universe is not full, it is overwhelmingly empty. Imagine collecting every galaxy that exists within the observable universe. Each of those galaxies contains billions or even hundreds of billions of stars. Around many of those stars orbit planets, moons, asteroids, clouds of gas and dust, and countless microscopic particles. All of that combined represents everything we normally think of as the universe. Now imagine compressing all of that matter together. If you could gather every star, every planet, every grain of cosmic dust and squeeze them into a single region, the result would occupy only a tiny fraction of the space that exists. The overwhelming majority of the cosmos would remain empty. In fact, the average density of the universe is almost impossible to imagine. On average, there are only about a few hydrogen atoms in each cubic meter of space. A cubic meter is roughly the volume of a household washing machine. Inside that entire space, on average, you would find only a handful of particles. Compare that to the air around you right now. Every breath you take contains trillions upon trillions of molecules. Even the emptiest vacuum chambers scientists can create on Earth still contain far more particles than the depth of intergalactic space. In other words, the most perfect vacuum we can engineer in a laboratory is still crowded compared to the universe. The cosmos is less like a solid structure and more like an enormous ocean with a few scattered islands. Our galaxy, the Milky Way, is one of those islands. Inside it, hundreds of billions of stars swirl together in a vast spiral structure stretching more than 100,000 light-years across. Around many of those stars orbit planetary systems. From inside this crowded environment, it can feel as though space must be full of objects. But once you travel beyond the boundaries of the galaxy, the illusion disappears. Between galaxies lies an expanse so empty that even the nearest neighbours are unimaginably far apart. The closest large galaxy to us, the Andromeda Galaxy, is about 2.5 million light-years away. That distance is so vast that if you could travel at the speed of light, faster than anything humans have ever built, the journey would still take millions of years, and Andromeda is considered close. Beyond it, the distances grow dramatically larger. Galaxy clusters may contain hundreds or thousands of galaxies, but even within those clusters, the gaps between galaxies are enormous. Then there are the spaces between clusters themselves, where the universe becomes quieter still. The scale of these empty regions defies human intuition. To understand it, imagine shrinking the Milky Way down until it is the size of a coin. At that same scale, the nearest galaxy would still be several meters away, and the next galaxy cluster might be kilometers distant. Space is not packed tightly with galaxies. They are scattered sparsely across a vast and mostly empty cosmic landscape. early astronomers had only a limited view of this reality. When they looked through their telescopes, they saw bright stars and glowing nebulae. Later, they discovered distant galaxies, entire island universes scattered across the sky. For a long time, it seemed as though galaxies might be distributed somewhat randomly, like grains of sand scattered across a beach. But as technology improved, astronomers began mapping the positions of galaxies across enormous regions of space. One of the most ambitious efforts to do this was the Sloan Digital Sky Survey, a project that measured the distances and locations of millions of galaxies across billions of light years. The map that emerged revealed something astonishing. Galaxies were not spread evenly across the universe. Instead, they formed an immense structure stretching across the cosmos, a network of filaments and walls surrounding enormous empty regions. Astronomers began calling this pattern the cosmic web. If you could step outside the universe and look down on this structure from afar, you might see something resembling a gigantic three-dimensional spider web. Bright threads of galaxies would stretch across space, intersecting at dense knots where clusters of galaxies gather together. But the most striking feature of this structure is not the threads themselves. It is the vast empty bubbles between them. These bubbles, known as cosmic voids, dominate the universe. Some of them stretch across hundreds of millions of light years. Inside these regions, galaxies are extremely rare. In certain voids, you could travel tens of millions of light years in any direction without encountering another galaxy at all. To someone living in one of those regions, the universe might appear almost completely dark. From our vantage point within a galaxy cluster, the night sky appears rich with distant galaxies visible through powerful telescopes. But if our Milky Way were located deep inside a cosmic void, that view would change dramatically. The sky would contain far fewer galaxies. The universe might appear far smaller than it truly is. Entire regions of cosmic structure would remain hidden beyond the darkness. This realization has profound implications. The universe is not just large, it is structured around emptiness. Matter gathers along delicate filaments while enormous regions of space remain almost completely devoid of it. The architecture of the cosmos is defined not only by what exists, but by what does not. In fact, most of the volume of the universe lies inside these voids. Imagine the foam on top of a wave crashing onto the shore. The bubbles in that foam are mostly empty space, surrounded by thin walls of water. The cosmic web is similar. The filaments and galaxy clusters form the thin boundaries around enormous bubbles of nothing. And these bubbles are not static, they're growing. As the universe expands, matter slowly flows away from the centers of voids and gathers along the surrounding filaments. Gravity pulls galaxies toward denser regions, leaving the interiors of voids emptier over time. The more empty a void becomes, the faster it tends to expand. In a strange way, emptiness feeds on itself. Regions with less matter experience weaker gravitational pull, allowing the expansion of space to stretch them more rapidly. Over billions of years, this process gradually pushes galaxies farther apart, widening the cosmic voids between them. The result is a universe where islands of matter drift slowly away from one another, across an ever-expanding sea of emptiness. But this raises an important question. Why does the universe expand at all? Why does space continue stretching, carrying galaxies farther apart with every passing moment? For decades, scientists believed gravity alone controlled the fate of the cosmos. The combined mass of galaxies should gradually slow the expansion of the universe, perhaps even reversing it one day in a dramatic collapse. But when astronomers looked deeper into space and measured the motion of distant galaxies, they discovered something profoundly unexpected. The expansion of the universe is not slowing down, it is accelerating. Something within the emptiness of space itself appears to be pushing the universe apart. and that mysterious force may explain why the universe is becoming increasingly empty. To understand the true reason the cosmos is dominated by vast voids, we must look beyond galaxies, beyond gravity, and into one of the greatest mysteries in modern physics, a force hidden inside the fabric of space itself, a force scientists call dark energy. If the universe were completely random, galaxies would be scattered through space the way grains of sand scatter across a desert. No patterns, no structure, just an endless distribution of matter drifting through the void. For a long time, that was roughly how scientists imagined the cosmos. Early telescopes revealed stars in our own galaxy, and later observations uncovered other galaxies spread across the sky. The universe appeared vast and populated, but its deeper structure remained hidden. It was only when astronomers began mapping galaxies across truly enormous distances that a surprising pattern emerged. The universe is not random. Instead, galaxies form one of the largest structures known to science, an immense, interconnected framework stretching across billions of light years. Astronomers call this structure the cosmic web. To understand what this looks like, imagine a gigantic three-dimensional spiderweb woven across the universe. The thin threads of that web are made of galaxies, vast rivers of stars bound together by gravity. Where multiple threads intersect, enormous clusters of galaxies gather, creating bright nodes of cosmic activity. Between these threads lie vast empty bubbles. The cosmic web is not defined by what fills space, but by the enormous regions where almost nothing exists. These regions are the cosmic voids. The discovery of this structure did not happen overnight. It emerged gradually as astronomers improved their ability to measure the distances to galaxies. Mapping galaxies in 3 dimensions requires more than simply knowing where they appear in the sky. Scientists also need to know how far away they are. One of the most ambitious efforts to accomplish this was the Sloan Digital Sky Survey, a massive project that began in the early 2000s. Using a dedicated telescope, astronomers measured the positions and distances of millions of galaxies across huge volumes of space. When those measurements were combined into a single map, the result was astonishing. Instead of a uniform spread of galaxies, the universe revealed a vast network of filaments stretching across cosmic space. These filaments form walls and strands surrounding gigantic empty cavities. The pattern resembles soap bubbles pressed together in foam. Each bubble represents a cosmic void, a massive region of space with very few galaxies inside. The thin surfaces where bubbles meet contain the filaments and clusters that hold most of the universe's visible matter. This structure spans unimaginable distances. Some of the filaments stretch across hundreds of millions of light years. The largest galaxy clusters contain thousands of galaxies bound together by gravity, and the voids between them can be even larger, forming cosmic caverns where the density of matter drops to nearly nothing. If you could zoom out far enough to see the universe on the larger scales, you would not see a chaotic scatter of galaxies. You would see a vast network, a glowing web suspended in darkness. But how did such an enormous structure form? The answer lies in the earliest moments after the birth of the universe. Shortly after the Big Bang, the universe was incredibly hot and dense. Matter and radiation were mixed together in a nearly uniform cosmic soup. On large scales, the distribution of matter was remarkably smooth. But it was not perfectly smooth. Tiny fluctuations existed. Small regions where the density of matter was slightly higher or slightly lower than average. These variations were extremely subtle, perhaps 1 part in 100,000. Over time, gravity amplified those tiny differences. Regions with slightly more matter exerted stronger gravitational pull, drawing additional matter toward them. As more matter accumulated, those regions grew denser and heavier, attracting even more material. Meanwhile, regions that started with slightly less matter gradually lost material to their denser neighbours. Over billions of years, this process slowly sculpted the universe. Dense regions collapsed into galaxies and clusters. Less dense regions became increasingly empty. The result of this long gravitational evolution is the cosmic web we observe today. Computer simulations of cosmic evolution confirm this picture. When scientists run simulations that begin with the conditions measured shortly after the Big Bang and allow gravity to shape matter over billions of years, the resulting universe naturally forms a web-like pattern, almost identical to what we observe. Galaxies gather along thin filaments, clusters appear at intersections, and enormous voids expand between them. But while gravity helps explain how this structure formed, it does not fully explain why the voids are so large, or why they continue growing. As the universe expands, something unusual happens inside these empty regions. Gravity becomes weaker. Inside dense galaxy clusters, gravity pulls galaxies together and helps keep them bound. But inside the voids, there is very little matter to exert gravitational attraction. Without gravity pulling things inward, the expansion of space can stretch these regions more freely. Over time, galaxies slowly drift toward the denser edges of the cosmic web. This leaves the centers of voids even emptier than before. In other words, the cosmic web evolves in a way that makes emptiness more extreme. Matter flows outward from the voids and gathers along the surrounding filaments, while the voids themselves expand and grow. Imagine pouring water across a flat landscape filled with shallow depressions. Over time, the water drains away from the high points and collects in the lowest areas. The high regions become dry and empty, while the valleys fill with rivers and lakes. The cosmic web behaves in a somewhat similar way. Matter drains away from the voids and accumulates along the filaments and clusters, leaving enormous bubbles of near vacuum behind. These voids are not just large, they dominate the universe. Although galaxies and clusters contain most of the visible matter, they occupy only a tiny fraction of cosmic space. The majority of the universe's volume lies inside the voids. This means that the most common environment in the universe is not a galaxy, a star system, or even intergalactic space near galaxies. It is the interior of a cosmic void, a place where galaxies are rare, distances are immense, and darkness stretches for hundreds of millions of light years. But even this enormous structure, the cosmic web itself, is not permanent. The expansion of the universe continues stretching space in every direction. As this expansion accelerates, the filaments connecting galaxy clusters are slowly pulled apart. The cosmic web, once tightly woven by gravity, is gradually loosening. Over billions of years, clusters of galaxies will become increasingly isolated from one another. The filaments between them will stretch thinner and thinner until the connections eventually disappear. The universe will slowly transform into a collection of isolated islands of matter, drifting through expanding space. Between those islands will lie the growing voids. The cosmic web is the universe's largest structure today, but even it may not survive forever, because the same force driving the expansion of space is also widening the voids. The emptiness between galaxies is not static, it is spreading, and the more it spreads, the more dominant it becomes. To understand just how extreme this emptiness can become, astronomers have begun studying some of the largest voids ever discovered, regions so vast and empty that they challenge our understanding of how the universe evolved. One of these regions contains almost nothing at all, a cosmic cavity so enormous that it should barely exist, and yet it does. If the cosmic web is the skeleton of the universe, then the voids are its vast empty lungs, enormous cavities where matter has almost completely disappeared. At first glance, the word void might suggest a simple gap between galaxies, something like the empty space between houses in a quiet neighborhood. But the reality is far more dramatic. Cosmic voids are not small spaces between structures. They are the largest known regions in the entire universe. Some of them stretch across hundreds of millions of light years. To appreciate the scale of this emptiness, imagine travelling across one of these voids at the speed of light, the fastest possible speed in the universe. Even then, the journey could take longer than the entire history of human civilization. In many cases, it would take longer than complex life has existed on Earth. Inside these regions, galaxies are astonishingly rare. While galaxy clusters might contain thousands of galaxies packed together by gravity, a void may contain only a few scattered systems drifting alone through the darkness. In some cases, the density of matter drops so low that astronomers struggle to find anything at all within these regions. One of the most famous examples is known as the Bhooter's Void, sometimes called the Great Nothing. This vast region of space was discovered in 1981 by astronomers studying the distribution of galaxies in the constellation Bhooter's. When they mapped the positions of galaxies across that region of the sky, they noticed something strange. There was an enormous spherical area where almost no galaxies existed. Further observations confirmed the discovery. The Bhooter's Void stretches roughly 330 million light-years across. Within that immense region, astronomers have found only a few dozen galaxies, far fewer than expected. To understand how unusual that is, consider what normally occupies such a large volume of space. A region that size should contain thousands of galaxies. Instead, the Bhooter's Void contains almost none. If our own galaxy happened to lie near the centre of this void, the night sky would look profoundly different from the one we see today. Instead of a universe filled with distant galaxies visible through powerful telescopes, astronomers might see almost nothing at all. The cosmic web would remain hidden beyond an immense wall of darkness. For a long time, discoveries like this seemed puzzling. According to early cosmological models, the universe should contain empty regions, but not ones quite this large or quite this empty. Yet as galaxy surveys improved, astronomers began finding more voids scattered throughout the cosmic web. Some are smaller than the Bhooter's Void, while others rival it in scale. One of the largest structures ever discovered is the Eridanus supervoid, a gigantic region of unusually low matter density located in the direction of the constellation Eridanus. This void may span nearly 1 billion light-years across, a scale so enormous that it challenges our ability to visualize it. Inside this immense cosmic depression, galaxies are much less common than in surrounding regions. But the Eridanus supervoid revealed something even more surprising. When scientists examined the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang, they noticed a strange cold spot in that same region of the sky. The radiation passing through the supervoid appeared slightly cooler than expected. This phenomenon occurs because of something called the integrated Sachs-Wolf effect. As photons from the cosmic microwave background travel across the universe, they pass through enormous gravitational landscapes created by clusters of galaxies and vast voids. When radiation enters a dense region of space, gravity pulls on the photons, slightly increasing their energy. When it leaves that region, it loses that energy again. But in a universe where expansion is accelerating, the situation becomes slightly asymmetric. If photons pass through a massive void that is expanding rapidly, they lose a tiny bit of energy during the journey. The result is a slight cooling of the radiation, a small but measurable temperature difference. The cold spot associated with the Eridanus supervoid may be one of the most dramatic examples of this effect ever observed. It is a reminder that voids are not merely empty regions. They actively shape the way light and matter move through the universe. In fact, voids play an important role in cosmic evolution. Because they contain so little matter, gravity inside these regions is extremely weak. This allows the expansion of space to stretch them more rapidly than surrounding regions filled with galaxies. Over time, matter flows outward from the centers of voids and accumulates along the filaments of the cosmic web. Imagine a shallow basin surrounded by hills. If water were poured into that landscape, it would gradually drain away from the high ground and collect in the valleys. The high regions would grow dry while the valleys filled with streams and lakes. In a similar way, matter slowly drains away from cosmic voids. Galaxies drift toward the dense filaments surrounding them, leaving the interiors increasingly empty. As this happens, the voids expand even further. This process has been confirmed through detailed cosmological simulations. When scientists model the growth of the universe using the laws of gravity and the observed distribution of dark matter, the simulations naturally produce the same expanding voids we observe in reality. Matter collapses into filaments, clusters form where filaments intersect, and the empty regions between them grow larger and emptier with time. But something else is happening inside those voids as well. A force far more mysterious than gravity is beginning to dominate their evolution. That force is dark energy. Inside dense galaxy clusters, gravity still holds matter together. The gravitational pull between galaxies is strong enough to resist the expansion of space. Even though the universe is expanding overall, structures like galaxies and clusters remain bound. But inside the voids, gravity has very little influence. There simply is not enough matter there to create strong gravitational attraction. Without gravity pulling things together, the expansion of space can stretch those regions almost freely. This means voids expand faster than the rest of the universe. As they grow, they push galaxies outward toward the filaments and clusters of the cosmic web. The more matter leaves a void, the weaker gravity becomes inside it, and the weaker gravity becomes, the faster expansion can stretch it. The emptiness feeds on itself. Over billions of years, this process transforms the universe into a more extreme version of the cosmic web we see today. The filaments grow thinner, the clusters become more isolated, and the voids grow ever larger. Eventually, these voids may dominate nearly all of cosmic space. Galaxy clusters will become distant islands surrounded by expanding oceans of darkness. The cosmic web itself will slowly unravel as expansion stretches the filaments connecting those islands. Over immense spans of time, the connections between clusters will disappear entirely. The universe will become a collection of isolated galaxies drifting through enormous regions of empty space. But the most unsettling part of this story is that the process is already underway. Every second, space continues to expand. Every billion years, galaxies drift farther apart, and every moment the voids between them grow wider. What began as tiny density fluctuations shortly after the Big Bang has evolved into a universe where emptiness dominates the largest scales of reality. But the true reason for this growing emptiness does not lie solely in gravity. It lies in the strange energy hidden within space itself, an energy that is quietly pushing the universe apart, and that energy may ultimately determine the fate of everything that exists. For most of the 20th century, astronomers believed they understood the broad story of the universe. In 1929, astronomer Edwin Hubble made one of the most important discoveries in the history of science. By measuring the light from distant galaxies, he found that almost all of them were moving away from us. The farther away a galaxy was, the faster it appeared to be receding. This observation revealed something revolutionary. The universe itself was expanding. Galaxies were not flying outward from a central explosion. Instead, space itself was stretching, carrying galaxies along like dots drawn on the surface of an inflating balloon. Once scientists accepted that the universe was expanding, the next question seemed straightforward. Would the expansion continue forever? Or would gravity eventually slow it down? Every galaxy pulls on every other galaxy through gravity. The combined mass of all the matter in the universe should act like a cosmic brake, gradually reducing the speed of expansion. In theory, if enough matter existed, gravity could even reverse the expansion entirely, causing the universe to collapse in a dramatic event sometimes called the Big Crunch. For decades, astronomers focused on measuring how quickly the expansion of the universe was slowing. But in the late 1990s, two independent teams of researchers set out to measure something slightly different. Instead of looking at nearby galaxies, they studied extremely distant Type Ia supernovae, powerful stellar explosions that shine with nearly identical brightness. Because these explosions behave like cosmic standard candles, astronomers can use them to measure enormous distances across the universe. The idea was simple. If the universe's expansion had been slowing down over time, then distant supernovae should appear slightly closer than expected. But when the data arrived, the results made no sense. The supernovae were farther away than they should have been. That meant the expansion of the universe had not been slowing down. It had been speeding up. The discovery stunned the scientific community. Instead of gravity gradually pulling the cosmos back together, some unknown force was pushing galaxies apart faster and faster. Something embedded within the fabric of space itself appeared to be accelerating the expansion of the universe. The researchers had uncovered one of the greatest mysteries in modern physics. They called this unknown force dark energy. The name itself reveals how little we truly understand about it. Dark energy does not glow, reflect light, or interact with matter in any obvious way. It cannot be captured in detectors or observed directly. The only reason we know it exists is because of the way the universe expands. Yet despite its invisibility, dark energy appears to dominate the cosmos. Careful measurements of the universe's energy budget reveal something astonishing. Only about 5% of the universe consists of ordinary matter, the atoms that make up stars, planets, gas, dust, and everything we can see. About 25% appears to be an invisible substance known as dark matter, which exerts gravitational pull but does not emit light. And the remaining 70% is dark energy. In other words, the vast majority of the universe is made of something we barely understand. To grasp how strange this is, imagine discovering that most of the ocean on Earth is made of a mysterious liquid that no one has ever directly observed, a substance that shapes the movement of waves but cannot be touched or measured in the usual ways. That is essentially the situation physicists face with dark energy. The leading explanation is that dark energy may be a property of space itself. According to Einstein's theory of general relativity, empty space is not truly empty. Even a perfect vacuum can contain energy, a tiny background energy embedded in the structure of space-time. This idea is known as the cosmological constant. Einstein himself introduced this concept more than a century ago while trying to construct a mathematical model of the universe. At the time, scientists believed the universe was static and unchanging. Einstein added a small repulsive force to his equations to counteract gravity and keep the universe from collapsing. But when Hubble discovered that the universe was expanding, Einstein reportedly called the cosmological constant his greatest blunder. For decades, scientists ignored the idea. Then the discovery of dark energy brought it back to life. If empty space itself contains energy, that energy could act like a kind of pressure pushing space outward. And unlike ordinary matter or radiation, this energy would not dilute as the universe expands. In fact, something very strange would happen. As the universe grows larger, more space appears. And if every cubic meter of space contains dark energy, then expanding space would create more dark energy. More space means more dark energy. More dark energy means stronger acceleration. And stronger acceleration creates even more space. The result is a self-reinforcing process, a feedback loop driving the expansion of the universe faster and faster. At first, the effect of dark energy was extremely small. In the early universe, matter was densely packed together. Gravity dominated the evolution of cosmic structure, pulling matter into galaxies, clusters, and the vast filaments of the cosmic web. But as the universe expanded and matter spread farther apart, gravity gradually weakened on large scales. Dark energy did not weaken. Because it is tied to space itself, its influence remained constant, or possibly even increased as more space formed. Billions of years after the Big Bang, dark energy began to take control. Today, it appears to dominate the large-scale dynamics of the cosmos. The expansion of the universe is accelerating, and that acceleration is driven by something that seems to be woven into the structure of space itself. But the effects of dark energy are not uniform everywhere. In regions where gravity is strong, inside galaxies and clusters, matter still holds itself together. Stars orbit the centers of galaxies. Galaxies remain bound inside clusters. Even though the universe expands overall, these local structures resist the stretching of space. Inside cosmic voids, however, the story is different. Void regions contain very little matter. That means gravity inside them is extremely weak. Without gravity pulling things inward, the expansion of space can stretch those regions more freely. Dark energy dominates the evolution of these vast empty areas, pushing them outward at accelerating speeds. In a sense, cosmic voids are the places where dark energy reveals itself most clearly. The emptier a region becomes, the more strongly dark energy influences its expansion. This is why the largest voids in the universe continue growing. They are not just empty spaces. They are regions where the expansion of the universe is most powerful. Over billions of years, this process slowly reshapes the cosmic web. Filaments stretch, galaxy clusters drift farther apart. The connections between them grow thinner and more fragile. Eventually, if dark energy continues to dominate, the cosmic web itself may begin to unravel. Clusters of galaxies will become isolated islands surrounded by expanding oceans of emptiness. The universe will grow darker, quieter, and more distant with time, but the most unsettling consequence of dark energy is not simply that space is expanding. It is that this expansion creates a boundary, a limit to what we can ever observe. Beyond that boundary lies a region of the universe we will never see. A region whose light can never reach us. A region that is already slipping beyond our cosmic horizon. And understanding that horizon changes the way we see the universe forever. When we look into the night sky, it feels as though we are seeing the entire universe spread out before us. With powerful telescopes, astronomers can observe galaxies billions of light years away. Some of the light entering our instruments today began its journey long before the Earth even formed. It is natural to assume that if we simply build better telescopes and wait long enough, we will eventually be able to see everything. But the universe does not work that way. There is a boundary to what we can observe, not because light hasn't had time to reach us yet, but because some light will never reach us at all. That boundary is called the cosmic event horizon. To understand why it exists, we need to think carefully about how the universe expands. When galaxies appear to move away from us, they are not travelling through space like rockets leaving a launch pad. Instead, the space between galaxies is stretching. Imagine drawing dots on the surface of a balloon and then inflating it. As the balloon expands, every dot moves away from every other dot, even though none of the dots are actually moving across the surface. This is essentially what happens in our universe. Space itself expands. Now consider what happens when that expansion continues accelerating. If a galaxy is far enough away, the space between us and that galaxy may expand faster than light can travel across it. This does not violate the laws of physics, because the galaxy is not moving through space faster than light. Instead, space itself is growing. And when space expands fast enough, something remarkable happens. Light leaving that distant galaxy can no longer make progress toward us. Imagine swimming upstream in a river. If the current is slow, you can move against it. If the current becomes stronger, you might still make progress, but only slowly. but if the current eventually becomes faster than you can swim, you will be carried backward no matter how hard you try. Light travelling through expanding space faces a similar challenge. At great enough distances, the expansion of space becomes like an accelerating current. Photons travelling toward us move forward locally, but the space they're crossing stretches even faster. The result is that the distance between us and the photon keeps increasing. The photon never arrives. This creates a boundary around us in the universe, a horizon beyond which events can never influence us. Anything beyond this horizon is permanently inaccessible. Even if a civilization in a distant galaxy built the most powerful beacon imaginable and pointed it directly at Earth, we would never see it if that galaxy lies beyond the cosmic event horizon. The signal could travel forever and still never reach us. Right now, this horizon lies roughly 16 billion light-years away. But that number is deceptive. The observable universe, the region we can currently see, is about 46 billion light-years in radius. That light left those galaxies billions of years ago, when they were much closer to us. Over time, as their light travelled through expanding space, the galaxies themselves continued moving away. Today, many of those galaxies lie far beyond the event horizon. We can still see them because their light began its journey long ago, but any new light they emit now will never reach us. In other words, we are watching ancient history. We are seeing galaxies as they were billions of years in the past, even though their present-day state is already hidden from us forever. This realization changes the way we think about the universe. When we look at a distant galaxy, we might assume it is still there in the same form we observe. But in reality, the galaxy we see may have evolved dramatically since that light began travelling toward us. It may have collided with other galaxies. It may have formed new stars. It may even have changed shape entirely. But we will never know. The current information cannot reach us, and the situation becomes even more dramatic over time. Because the expansion of the universe is accelerating, the cosmic event horizon is slowly moving inward relative to distant galaxies. More and more galaxies cross that boundary every year. Astronomers estimate that tens of thousands of galaxies become permanently unreachable every single year. Their light will never reach us again. From our perspective, they are slowly disappearing from the observable universe. Not because they are destroyed, but because space itself carries them away faster than light can bridge the gap. If this trend continues, and all evidence suggests it will, the universe of the far future will look profoundly different from the one we see today. Right now, the night sky contains billions of galaxies visible to modern telescopes. Astronomers can map enormous structures spanning billions of light-years across space. But billions of years from now, the situation will change dramatically. Galaxies beyond our local cosmic neighbourhood will drift farther and farther away. Eventually, their light will stretch so much that it becomes undetectable. One by one, those galaxies will slip beyond the cosmic event horizon. Future astronomers living trillions of years from now may look into the sky and see almost nothing. Only a handful of nearby galaxies will remain visible. Everything else will be gone. This will create a strange situation for any intelligent civilization that exists in that distant future. Without visible distant galaxies, those future scientists would have no evidence that the universe was ever larger than their local cluster of stars. They might conclude that their galaxy is the entire universe. The cosmic expansion we observe today would be impossible for them to detect. Even the faint afterglow of the Big Bang, the cosmic microwave background, will eventually stretch to wavelengths so long that it becomes undetectable. All the clues we currently use to understand the origin and evolution of the universe will disappear. In a sense, we are living during a unique moment in cosmic history. Right now, the universe is still young enough that we can see its large-scale structure. The cosmic web stretches across space. Distant galaxies reveal the expansion of the cosmos. The afterglow of the Big Bang still fills the sky. But this window will not last forever. Over immense spans of time, the observable universe will shrink. More and more galaxies will slip beyond the cosmic horizon. The universe will grow quieter and darker. Eventually, only the galaxies gravitationally bound to our own will remain visible, and everything else will be lost beyond the expanding ocean of space. But the cosmic event horizon does something even more unsettling. It does not only isolate galaxies, it isolates civilizations. If intelligent life exists in distant galaxies, the expansion of the universe may prevent us from ever meeting them. Even if advanced civilizations arise across the cosmos, they may remain forever separated by the expanding void between galaxies. The universe may be filled with life, but the cosmic horizon could ensure that most civilizations never know the others exist. Right now, when we look out into space, the universe appears enormous and richly populated. Modern telescopes reveal galaxies scattered across the sky in every direction. Deep-field images show thousands of galaxies packed into regions of space no larger than a grain of sand held at arm's length. To us, the cosmos looks full, but this view is temporary, because the same force that created the cosmic event horizon is slowly erasing most of the universe from view. At this moment, countless galaxies are already moving away from us so quickly that their light will never reach Earth again. We can still see them today only because the light we detect left those galaxies billions of years ago when they were much closer. But as time passes, that connection is gradually being severed. The expansion of the universe stretches light itself. As photons travel through expanding space, their wavelengths grow longer. Light that began as visible radiation can stretch into infrared, then into radio waves, and eventually into wavelengths so long that no detector can measure them. Astronomers call this process cosmic redshift. For nearby galaxies, the effect is small. Their light shifts slightly toward the red end of the spectrum as they move away from us. But for extremely distant galaxies, the effect becomes dramatic. Light that originally shone brightly across the visible spectrum becomes stretched so much that it fades into faint radio waves. Eventually, the wavelengths become so enormous that the radiation effectively disappears into the background noise of the universe. In other words, galaxies do not vanish instantly. They fade, slowly, gradually. Their light becomes more stretched and more diluted until it becomes impossible to detect. Over cosmic timescales, this process will transform the night sky. Billions of years from now, the universe will look very different to any civilization that still exists. Right now, the Milky Way is part of a larger collection of galaxies known as the Local Group. This group contains roughly 80 galaxies, including our large neighbours, the Andromeda Galaxy and the Triangulum Galaxy, along with dozens of smaller dwarf galaxies. These galaxies are close enough that gravity binds them together. Even though the universe expands overall, gravity inside the Local Group is strong enough to hold these galaxies in a slow, gravitational dance. In fact, the Andromeda Galaxy is actually moving toward us. In about 4 billion years, the Milky Way and Andromeda will collide and merge into a single massive galaxy. This cosmic collision may sound catastrophic, but in reality it will unfold slowly over millions of years. Most stars will pass by one another without ever colliding, because the distances between them are enormous. Eventually, the two galaxies will settle into a new structure, a giant elliptical galaxy containing perhaps 1 trillion stars. But beyond the Local Group lies a much larger region known as the Virgo supercluster, which contains tens of thousands of galaxies. And beyond that lies the even larger structure known as the Laniakea supercluster, a vast region spanning hundreds of millions of light years. At the moment, astronomers can observe these enormous structures clearly, but they will not remain visible forever, because galaxies outside the Local Group are not gravitationally bound to us strongly enough to resist cosmic expansion. Over time, dark energy will gradually push them farther and farther away. As billions of years pass, those distant galaxies will drift closer to the cosmic event horizon. Eventually they will cross it. Once they do, the light they emit can never reach us again. To observers in our galaxy, those galaxies will slowly disappear. First, the most distant galaxies will fade beyond detection. Then entire galaxy clusters will vanish. Later, even massive structures like the Virgo cluster will slip beyond the horizon. Over immense spans of time, the observable universe will shrink dramatically. Future astronomers living trillions of years from now may look into the sky and see only a single galaxy, the merged remnant of the Milky Way and Andromeda. No distant galaxies, no cosmic web, no visible evidence of the vast universe we observe today. Their universe would appear small and lonely. This creates one of the strangest consequences of cosmic expansion. Future civilizations may never discover the true history of the universe. Without distant galaxies to measure, they would have no way to detect cosmic expansion. Without the cosmic microwave background, which will eventually stretch beyond detectable wavelengths, they would have no evidence of the Big Bang. To them, the universe might appear eternal and unchanging. They would be living inside a small island of stars surrounded by endless darkness, and they might never realize that their galaxy was once part of a vast cosmic web filled with trillions of galaxies. In a sense, we are living at a special moment in cosmic history. Right now, the universe is old enough for complex structures to have formed. Galaxies exist. Stars shine. Planets orbit those stars. Life has emerged on at least one world. But the universe is also still young enough that we can see its large-scale structure. We can observe the expansion of space. We can measure the afterglow of the Big Bang. We can study galaxies billions of light-years away and reconstruct the history of the cosmos. This window of observation is temporary. Billions of years from now, that window will close. The universe will not end suddenly. Instead, it will quietly fade. Galaxies will drift away one by one, slipping beyond the horizon until the night sky grows darker with each passing age. Eventually, the universe will become a lonely place. A place where even the memory of its former vastness has been erased by the relentless expansion of space. And that raises an even deeper question. If the universe is filled with galaxies, and potentially billions of habitable planets, why do we see no signs of other civilizations among them? Because if intelligent life is common, the universe should already be full of it. Yet the cosmos remains strangely silent. Our galaxy alone contains an almost unimaginable number of stars. Current estimates suggest that the Milky Way holds around 400 billion of them. For most of human history, those distant points of light were simply mysteries, objects too far away to understand. Modern astronomy has changed that view completely. Over the past few decades, astronomers have discovered that planets are not rare accidents. Observations from space telescopes such as Kepler and TESS have revealed that planetary systems appear to form naturally around many stars. In fact, the data now suggests that planets may be more common than stars themselves. Billions of planets likely exist in our galaxy alone. Among them are worlds orbiting at distances where temperatures allow liquid water to exist. This region around a star is known as the habitable zone, sometimes called the Goldilocks zone, because conditions are neither too hot nor too cold. Liquid water is considered one of the most important ingredients for life as we understand it. On Earth, wherever water exists, from deep ocean vents to frozen polar ice, life has found a way to survive. Given that reality, the implications are extraordinary. If billions of planets exist in habitable environments, then the conditions that allowed life to emerge on Earth might exist elsewhere as well. Over billions of years, life could arise, evolve, and potentially develop intelligence on countless worlds across the galaxy. Now expand that idea further. The Milky Way is only one galaxy among hundreds of billions in the observable universe. Many of those galaxies contain hundreds of billions of stars of their own. Multiply those numbers together, and the potential number of habitable planets becomes almost impossible to comprehend. The universe should be full of life, at least that is what the numbers suggest. Yet when scientists search the sky, something strange becomes apparent. There are no obvious signs of advanced civilizations, no massive artificial structures surrounding distant stars, no networks of powerful interstellar transmissions, no spacecraft visiting our solar system. Despite decades of searching, the universe appears silent. This contradiction between expectation and observation is known as the Fermi paradox. The paradox takes its name from the physicist Enrico Fermi, who posed a simple question during a conversation with colleagues in 1950. If intelligent life is common in the universe, where is everybody? The question seems deceptively simple, yet the logic behind it is powerful. Consider the enormous age of the Milky Way galaxy. Stars have been forming here for more than 13 billion years. Our own sun is relatively young, forming about 4.6 billion years ago. That means countless other star systems had billions of years of head start before Earth even existed. If intelligent civilizations arose in those systems long ago, some of them might have developed advanced technology millions or even billions of years before humanity appeared. Given enough time, such civilizations could begin exploring neighboring stars. Even relatively slow spacecraft could gradually expand outward, colonizing nearby systems and then moving onward again. Over long periods of time, that expansion could spread across the entire galaxy. Surprisingly, the timescale required for such expansion is not very long by cosmic standards. Even if spacecraft travelled at only a small fraction of the speed of light, a civilization could potentially spread across the Milky Way in a few million years. Compared to the age of the galaxy, that is almost nothing. 13 billion years is more than enough time for many civilizations to rise, explore the galaxy, and leave detectable traces behind. But so far, nothing obvious has been found. Scientists have searched for artificial signals for decades. Radio telescopes around the world continuously scan the sky for unusual patterns that might indicate intelligent communication. Projects such as the Search for Extraterrestrial Intelligence, or SETI, analyse enormous volumes of radio data, looking for signals that cannot easily be explained by natural sources. At the same time, astronomers study distant stars for unusual behaviour that might suggest advanced technology. One idea involves looking for enormous structures built around stars to capture energy. A sufficiently advanced civilization might construct massive arrays of solar collectors, sometimes called Dyson spheres, capable of harvesting much of a star's power. Such structures could potentially be detected because they would alter the way a star emits light. So far, however, no confirmed examples have been found. Telescopes have also begun analysing the atmospheres of distant planets. Certain chemical combinations, particularly those produced by large-scale industrial activity, could reveal the presence of advanced civilizations, yet the results remain inconclusive. The deeper scientists search, the quieter the universe seems to be. Several explanations have been proposed for this silence. One possibility is that intelligent life is extremely rare. Perhaps the origin of life requires a very unusual set of circumstances. Maybe the leap from simple chemistry to living organisms occurs only rarely across the cosmos. Another possibility involves the evolution of complex life. On Earth, simple microbial life existed for billions of years before complex multicellular organisms appeared. The development of intelligence may depend on a long chain of unlikely events, each one narrowing the number of civilizations that could ever arise. Still another explanation is known as the Great Filter. This idea suggests that somewhere along the path from simple life to advanced civilization lies a barrier so difficult that almost no species manages to cross it. The filter might occur early in the process, preventing life from evolving beyond simple forms, or it might occur later. Technological civilizations could develop powerful tools capable of destroying themselves. Nuclear weapons, biological engineering, or artificial intelligence beyond their control, If most civilizations collapse shortly after reaching technological maturity, their existence might be brief on cosmic timescales. Another possibility involves distance itself. The universe is staggeringly large. Even travelling at a significant fraction of the speed of light, crossing the galaxy would take tens of thousands of years. Communication between distant civilizations might require enormous timescales as well. Signals travelling across interstellar distances weaken and disperse. Over enough distance, even powerful transmissions become indistinguishable from cosmic background noise. Cosmic expansion adds another complication. As galaxies drift farther apart, communication between them becomes increasingly difficult. Eventually, many galaxies will move beyond each other's event horizons, making contact physically impossible. Civilizations separated by enough distance may never know that the others exist. Isolation becomes inevitable. The silence of the universe may not mean life is absent. Instead, it may mean that every civilization exists on its own island of stars, separated from others by the immense and growing distances of the cosmos. From that perspective, humanity may simply be early in the story. Intelligent life might still be emerging across countless worlds, each one developing in isolation. If so, the universe may not be empty of life. It may simply be too vast and expanding too quickly for anyone to find their neighbours. The silence of the universe is not just puzzling, it is unsettling. When scientists first began considering the implications of the Fermi paradox, one possibility quickly emerged as both logical and disturbing. Somewhere between the formation of a planet and the rise of a civilization capable of exploring the stars, there may exist an obstacle so difficult that almost no species ever passes it. This hypothetical barrier is known as the Great Filter. The idea is simple but profound. Life does not evolve in a single step. It moves through a long sequence of stages, each one building upon the last. First, chemistry must produce self-replicating molecules. Then simple cells must form. Over time, those cells must evolve into complex organisms. Intelligence must appear. Technology must develop. Eventually, a civilization capable of space exploration might arise. Every stage in that sequence represents a challenge. If even one step is extremely unlikely, it could dramatically reduce the number of civilizations that ever emerge in the universe. To understand this idea, imagine a long corridor filled with doors. Behind the first door lies simple life. Behind the next lies complex life. Beyond that lies intelligence, technology, and eventually the stars themselves. If every door opens easily, then civilization should be everywhere. But if even one door is almost impossible to unlock, then very few species will ever reach the end of the corridor. That impossible door would be the Great Filter. One possibility is that the filter lies behind us. In that case, humanity may already have passed one of the rarest steps in the evolution of life. Perhaps the emergence of life itself is extraordinarily unlikely. The first self-replicating molecules might require a precise combination of conditions that rarely occurs on planetary surfaces. On Earth, life appeared surprisingly early in the planet's history. Evidence suggests that microorganisms existed within a few 100 million years after the planet cooled enough to support liquid water. But this does not necessarily mean life forms easily. Earth might simply be one of the rare places where the conditions happen to align. If the origin of life is extremely rare, then most planets in the universe may remain forever sterile. Another possibility involves the development of complex cells. For billions of years, life on Earth consisted only of simple microorganisms. These tiny organisms lacked internal structures and reproduced through relatively simple processes. Complex cells, known as eukaryotic cells, appeared much later. These cells contained specialized components such as mitochondria and nuclei, allowing them to support far more complicated biological functions. The origin of eukaryotic cells may have required a very unusual event. one primitive cell engulfing another and forming a stable partnership. If this process is extraordinarily rare, complex life could be extremely uncommon throughout the universe. Yet even complex life does not guarantee intelligence. For hundreds of millions of years, Earth was dominated by plants, insects, and simple animals. Dinosaurs ruled the planet for more than 150 million years without ever developing technology. Intelligence like that, possessed by humans, may be only one of many possible evolutionary outcomes, and perhaps not a common one. However, an even more unsettling possibility exists. The Great Filter might not lie behind us, it might lie ahead. This scenario suggests that intelligent civilizations often arise, but very few survive long enough to spread beyond their home planets. Technological progress brings enormous power, energy sources grow stronger, weapons become more destructive. Scientific discoveries open new possibilities and new dangers. A civilization capable of splitting the atom can produce both nuclear power plants and nuclear weapons. Advances in biology allow medicine to cure disease, but also make it possible to engineer new pathogens. Artificial intelligence offers the potential for extraordinary progress, yet also raises profound questions about control and safety. A species that gains advanced technology must learn to manage its power responsibly. If it fails, the consequences could be catastrophic. Self-inflicted disasters are not the only threats. Planets themselves are fragile environments. Climate change, environmental degradation, or resource depletion could destabilize civilizations before they ever reach the stars. Even natural cosmic events pose dangers. Nearby supernova explosions could bathe entire planetary systems in radiation. Gamma-ray bursts, the most powerful explosions in the universe, might sterilize large regions of space if one occurred close enough. Over billions of years, such events could repeatedly reset the progress of life on countless worlds. If civilizations tend to destroy themselves or succumb to cosmic disasters before expanding into space, then the universe could be filled with the ruins of extinct societies. Their existence might be brief compared to cosmic timescales. Signals from their civilizations could fade long before reaching distant stars. Artifacts left behind might erode away over millions of years. By the time a new civilization emerges elsewhere, the traces of earlier ones could be gone. The galaxy might be filled with the ghosts of civilizations that rose and fell long before humanity existed. Yet another possibility shifts the focus away from biological limits and toward physics itself. Interstellar travel may simply be far more difficult than imagined. The speed of light places strict limits on how quickly anything can move through space. Even traveling at enormous speeds, journeys between stars would take decades, centuries, or longer. The resources required for sustained interstellar exploration might be far greater than any civilization is willing or able to commit. Instead of spreading outward across the galaxy, advanced societies might focus inward, exploring virtual worlds, developing artificial environments, or simply choosing not to expand. In that case, the silence of the universe would not be caused by extinction or isolation. It would be caused by restraint, but the truth remains unknown. The Great Filter may lie behind us, meaning humanity is extraordinarily fortunate to have reached this stage of development. Or it may lie ahead, representing a challenge that no civilization has yet managed to overcome. Either way, the silence of the universe carries a powerful message. Across billions of stars and billions of years, something has prevented intelligent life from filling the galaxy. And if the Great Filter still waits somewhere in humanity's future, then the most difficult test for our species may not yet have arrived. The universe may contain countless worlds where life has emerged. Some of those worlds may have produced intelligent species capable of building cities, developing science, and looking up at their own night skies with curiosity. Yet even if civilizations arise across the cosmos, they may never encounter one another. Not because life is rare, not because intelligence fails to evolve, but because the universe itself may prevent contact. The distances between stars are already immense. Even the closest star system to our Sun, Alpha Centauri, lies more than 4 light-years away. A spacecraft travelling at the speed of today's fastest probes would require tens of thousands of years to reach it. And Alpha Centauri is practically next door. Most stars in our galaxy lie dozens, hundreds, or thousands of light-years apart. Crossing those distances requires technology far beyond anything humanity currently possesses. Still, those journeys are not impossible in principle. If a civilization developed spacecraft capable of travelling at even a small fraction of the speed of light, it could gradually expand outward from its home system. Colonies could form around nearby stars, and from those new outposts further exploration could begin. Over millions of years, such expansion might spread across the entire galaxy. But even this scenario faces enormous challenges. Travel between stars would demand extraordinary resources. Spacecraft would need to sustain life for decades or centuries. Generation ships might carry multiple lifetimes of travelers before reaching their destinations. Alternatively, robotic explorers might venture ahead, preparing distant worlds for future settlement. These ideas are not beyond the laws of physics, yet they remain daunting. Interstellar space is vast, cold, and filled with hazards. Microscopic dust particles travelling at enormous speeds could damage spacecraft. Radiation from distant stars and cosmic sources could threaten both machines and living organisms. But the greatest obstacle may not be the difficulty of travel, it may be time. Civilizations, like species, may not last forever. Human civilization has existed for only a few thousand years, an instant compared to the age of the galaxy. Even our modern technological society is barely more than a century old. A civilization that survives for 1,000,000 years would already be extraordinarily long-lived. Yet the galaxy has existed for more than 13 billion years. Over such immense timescales, civilizations may appear and disappear like brief flashes of light. One species might rise, develop technology, and vanish millions of years before another even begins its evolutionary journey. By the time the second civilization emerges, the first could already be gone. Signals sent across interstellar space take time to travel. A message transmitted from one side of the galaxy could require 100,000 years to reach the other side. During that time, entire civilizations might rise and fall. Even if intelligent life appears frequently, the chances that two civilizations exist at the same time and close enough to communicate may be surprisingly small. This creates what scientists sometimes call the cosmic timing problem. Life may be scattered throughout the galaxy, but civilizations could be separated not only by distance, but by time. One world might have hosted intelligent life billions of years ago. Another might not develop intelligence for billions of years yet to come. They would never overlap. They would never know about one another. Cosmic expansion adds another layer of isolation. Within our galaxy, gravity holds stars together in a massive rotating structure. The Milky Way remains bound despite the expansion of the universe. In principle, civilizations within the same galaxy could eventually reach one another, but the same cannot be said for civilizations in other galaxies. The distance between galaxies is already immense, often measured in millions of light years. On top of that, the expansion of the universe continues to push galaxies farther apart. Over time, this expansion accelerates. Galaxies outside our local gravitational neighborhood drift away faster and faster. Eventually, many of them cross the cosmic event horizon, becoming permanently unreachable. Any civilization that arises in these galaxies will remain forever isolated from us. Even if both civilizations possess advanced technology, the expanding universe prevents them from ever meeting. Communication becomes impossible. travel becomes impossible. Two intelligent species may exist simultaneously in different galaxies, yet remain separated forever by the growing void between them. This cosmic isolation may explain part of the Great Silence. The universe is not simply large, it is also growing larger with time. Distances that once allowed communication may become impossible to cross. Signals that might have reached us billions of years ago may now be stretched into undetectable wavelengths. The expansion of space quietly erases opportunities for contact. From this perspective, civilizations may resemble islands scattered across an enormous ocean. Each island contains its own inhabitants, its own culture, its own history. But the waters between them are so vast that ships rarely cross from one island to another. Over time, the ocean grows wider. Eventually, every island becomes isolated. Yet this raises a deeper question. Humanity exists during a particular moment in cosmic history. The universe is old enough for stars, planets, and life to have formed. At the same time, galaxies remain close enough that their light still reaches us. But this situation will not last forever. In the distant future, galaxies will slip beyond the cosmic horizon and the universe will become increasingly empty. If intelligent life arises in those distant galaxies later, they may never know that other civilizations ever existed elsewhere. Their sky will show only their own stars. The vast cosmic web we see today will already be gone. And this realization leads to an unsettling possibility. Perhaps we are not alone in the universe. Perhaps we are simply too far apart, too separated by distance, too separated by time, and too separated by the expanding void between galaxies to ever meet. The universe we see today is filled with light. Stars burn in every direction across the night sky. Galaxies glow with billions of suns. Nebulae shimmer with clouds of gas and dust where new stars are being born. From our vantage point in cosmic history, the universe appears vibrant and active. But this bright era will not last forever. Every star in the universe is powered by a limited supply of fuel. Deep inside their cores, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy in the process. That energy produces the light and heat that shine across space. Yet hydrogen is not infinite. Over time, stars slowly consume their fuel. When the hydrogen in a star's core runs out, the delicate balance between gravity and pressure collapses. The star changes dramatically. Some swell into enormous red giants before shedding their outer layers. Others explode as supernovae scattering heavy elements across space. Eventually, every star reaches the end of its life. For massive stars, that ending can arrive in only a few million years. Smaller stars like our Sun burn more slowly and can survive for billions of years. The smallest stars in the universe, red dwarfs, are the most patient of all. These dim stars burn their hydrogen so slowly that some may survive for trillions of years. Even so, they will eventually fade. For now, the universe continues producing new stars. Inside galaxies, vast clouds of gas slowly collapse under gravity. As these clouds compress, their centers heat up until nuclear fusion ignites, creating new stars. Entire regions of space glow with stellar nurseries where young stars are forming. But the rate of star formation is already declining. Billions of years ago, galaxies were far more active. The universe experienced a period known as cosmic noon, when star formation reached its peak. During that era, galaxies produced stars at a rate several times higher than they do today. Since then, the pace has slowed. Gas, the raw material required to form new stars, is gradually being used up. Some of it becomes locked inside long-lived stars. Some is expelled from galaxies during violent supernova explosions, or blown away by powerful jets from supermassive black holes. With each passing billion years, the reservoirs of star-forming gas grow smaller. Astronomers estimate that within about 1 trillion years, most galaxies will run out of the cold gas needed to create new stars. The cosmic era of star formation will effectively come to an end. After that point, the universe will enter a new phase. No new stars will appear. The galaxies that remain will contain only the stars that already exist. At first, many stars will still shine. Red dwarfs, the most common stars in the universe, will continue burning their hydrogen slowly for trillions of years. These faint stars will dominate the universe's remaining light long after larger stars have disappeared. But even red dwarfs cannot shine forever. Eventually their hydrogen fuel will be exhausted. When that happens, they will collapse into dense stellar remnants known as white dwarfs, small hot objects roughly the size of Earth, but containing the mass of a star. White dwarfs no longer produce energy through fusion. Instead, they slowly radiate away the heat left over from their earlier lives. Over immense spans of time, they cool and fade. After trillions upon trillions of years, these remnants will become black dwarfs, cold, dark spheres of inert matter drifting through space. By this stage, the universe will already look dramatically different. Galaxies will no longer contain bright stellar nurseries or massive blue stars blazing across the sky. Instead, they will be filled with aging stars and stellar corpses slowly cooling in the darkness. Occasionally, gravity will still cause interesting events. White dwarfs passing too close to one another may collide, producing rare supernova explosions even in this late era of cosmic history. Neutron stars, incredibly dense objects formed from collapsed stellar cores, may merge and release brief flashes of energy. But such events will become increasingly rare. With no new stars forming, the universe will gradually grow dimmer. Eventually, the last red dwarfs will burn out. When that happens, the familiar era of stars will finally end. The cosmos will enter what astronomers sometimes call the degenerate era, a time dominated not by shining stars but by the remnants they leave behind. The galaxies of that distant future will be filled with cold white dwarfs, neutron stars and black holes. Without bright stars illuminating the sky, space will become far darker than anything we can experience today. From the perspective of any observer living during that time, the universe would appear almost completely black. The only visible objects might be faint glowing remnants or occasional flashes from rare cosmic collisions. Yet even these remnants will not last forever. Gravity will slowly reshape the structure of galaxies over unimaginable spans of time. Stars and stellar remnants passing near one another may exchange energy, causing some objects to be ejected into intergalactic space. Galaxies will gradually lose their members, one by one, as objects drift away into the vast darkness between galaxies. Black holes will grow as they swallow nearby stars and remnants. Over time, these black holes will become the dominant structures in the universe, but even they are not eternal. A discovery made by the physicist Stephen Hawking in the 1970s revealed something astonishing. Black holes slowly emit radiation through quantum effects near their event horizons. This phenomenon, known as Hawking radiation, causes black holes to lose mass extremely slowly. For stellar mass black holes, the process takes an enormous amount of time. For the supermassive black holes at the centres of galaxies, the timescale is almost incomprehensible, around 10 to the power of 100 years before they evaporate completely. Yet even those giants will eventually disappear. When the last black hole evaporates, the universe will enter its final stage, a stage where almost nothing remains. By that time, galaxies will have dissolved, stars will be gone, black holes will have vanished. The cosmos will consist of a thin sea of elementary particles drifting through ever-expanding space. No new structures will form, no new stars will ignite. Energy will be spread so evenly that no processes capable of producing light or complexity can occur. Physicists call this ultimate fate heat death. It represents a universe that has reached maximum entropy. a state where energy differences have disappeared and nothing meaningful can happen anymore. The bright era of stars, galaxies, and life will have been only a brief chapter in cosmic history. But before the universe reaches that silent ending, another possibility must be considered, because the force driving cosmic expansion may not remain constant forever. If dark energy grows stronger over time, the universe might not fade quietly into darkness. Instead, it could be torn apart in a far more violent way. So far, the most likely future of the universe appears to be slow and quiet. Stars fade, galaxies drift apart, and over unimaginable spans of time the cosmos settles into a cold and motionless state. But that outcome depends on one critical assumption. It assumes that dark energy remains constant. If dark energy behaves exactly as current observations suggest, acting like a steady property of empty space, then the expansion of the universe will continue accelerating gently forever. Galaxies will drift apart, stars will eventually burn out, and the universe will fade into heat death. Yet scientists cannot be completely certain that dark energy behaves this way. Measurements show that dark energy is extremely close to a constant value, but the possibility remains that its strength could change over time, and if dark energy grows stronger as the universe ages, the consequences could be dramatic. In that scenario, the expansion of space would accelerate faster and faster. At first, the change might seem subtle. Galaxies would drift apart slightly faster than expected. The cosmic voids between clusters would widen more rapidly. But as the strength of dark energy increased, its effects would eventually overwhelm gravity on ever smaller scales. This theoretical scenario is known as the Big Rip. To understand how it works, imagine that the expansion of space gradually becomes more aggressive. In the present universe, dark energy influences only the larger scales. It pushes entire galaxies apart but has almost no effect inside galaxies themselves. Gravity inside galaxies is strong enough to hold stars together. Stars themselves remain stable, because the forces binding their atoms are vastly stronger than cosmic expansion. But if dark energy becomes stronger over time, that balance begins to change. First, the largest structures in the universe would begin to dissolve. Galaxy clusters, enormous systems containing hundreds or thousands of galaxies, are held together by gravity. But in a universe where dark energy grows increasingly powerful, even the gravity of these clusters would eventually fail to keep them bound. Clusters would begin to fall apart. Galaxies would drift away from one another as the expanding fabric of space stretches the distances between them. At this stage, the universe would still look relatively familiar. Galaxies themselves would remain intact, but the cosmic web connecting them would be gone. Each galaxy would become an isolated island drifting through an ever-growing sea of emptiness. As dark energy continues strengthening, the next stage begins. Galaxies themselves would begin to unravel. The stars orbiting within galaxies are held in place by gravity. But if the expansion of space grows strong enough, even those gravitational bonds could eventually be overcome. Stars at the outer edges of galaxies would drift away first. Spiral arms would slowly unwind. The galaxy structure would gradually dissolve as its stars scatter into intergalactic space. Eventually, even the central regions of galaxies would lose their cohesion. Stars would drift apart until each one travelled alone through the expanding void. For a while, planetary systems would still exist. Stars would continue shining, planets would continue orbiting them. But the expansion would not stop there. As dark energy grows even stronger, its influence would reach smaller scales. Planetary systems would begin to destabilize. The gravitational pull holding planets in orbit around their stars would weaken relative to the accelerating expansion of space. One by one, planets would slip free of their orbits and drift away into darkness. Eventually, only isolated stars would remain. Then the final stages would begin. As the expansion accelerates further, even stars themselves would no longer be safe. the force stretching space would begin pulling apart the gas and plasma inside stellar bodies. Stars would be torn apart. Matter once held together by gravity would scatter outward, unable to resist the growing expansion of space, and the destruction would not stop there. Atoms themselves depend on forces that hold their components together. Electrons orbit atomic nuclei because of electromagnetic attraction. Inside the nucleus, powerful forces bind protons and neutrons together. In a universe undergoing a big rip, even these forces could eventually be overwhelmed. Space itself would stretch so violently that atoms could no longer remain intact. Electrons would be pulled away from their nuclei. Atomic nuclei would split apart. Subatomic particles would scatter into the expanding void. At the final moment of the Big Rip, the fabric of space would be stretching so rapidly that no structure of any kind could survive. Galaxies would be gone, stars would be gone, planets, atoms and particles would all be torn apart. The universe would not fade into quiet darkness, it would be ripped apart. Fortunately, current observations suggest that this catastrophic scenario is unlikely. Measurements of dark energy indicate that its strength is extremely close to a constant value. If that measurement is correct, the expansion of the universe will continue accelerating, but not violently enough to destroy galaxies or atoms. Instead, the cosmos will drift slowly toward heat death. Still, uncertainty remains. The exact nature of dark energy is one of the greatest mysteries in physics. Scientists know how it behaves today, but they do not yet understand what it actually is. And without that knowledge, the long-term fate of the universe cannot be predicted with complete certainty. The Big Rip may never happen, but it remains one of several possibilities allowed by the laws of physics, and there is another possibility even stranger than a universe torn apart by expansion. Because the vacuum of space itself may not be stable. If that is true, the universe could end not in trillions of years, but in a single instant. So far, every possible ending of the universe we've explored unfolds across unimaginable spans of time. Trillions of years pass as stars fade. Quadrillions of years may follow before the last remnants of matter grow cold. Even the evaporation of black holes requires timescales so large that they barely fit within human imagination. But there is another possibility, one that does not require trillions of years, one that could happen at any moment. According to modern physics, the vacuum of space, the very fabric of reality itself, may not be completely stable. To understand this idea, we need to step into the strange world of quantum fields. In modern physics, particles are not truly separate objects floating through space. Instead, they are small disturbances in underlying fields that fill the universe. The electron is a ripple in the electron field. Photons are vibrations in the electromagnetic field. Every type of particle corresponds to its own field extending throughout space. Even when space appears completely empty, those fields still exist. They have a lowest possible energy state known as the vacuum state. For many years, scientists assumed that the vacuum state of our universe represented the absolute lowest possible energy configuration, the deepest valley in the landscape of physical reality. But theoretical work in particle physics suggests something more complicated. Our vacuum might not be the deepest valley. Instead, it might be a false vacuum, a temporary state that appears stable, but actually sits on a higher plateau, with a deeper valley somewhere else in the landscape. A useful analogy is a ball resting in a shallow depression on the side of a hill. At first glance, the ball seems stable. It does not roll anywhere, it remains in place. But the position is only stable because the ball has not yet been pushed over the edge. If a disturbance nudges the ball hard enough, it could roll down into a much deeper valley. The same idea may apply to the universe itself. If our vacuum is only metastable, meaning stable for long periods but not permanently, then a transition to a lower energy state could occur. Physicists call this event vacuum decay. If vacuum decay ever began, It would start in a tiny region of space where the field suddenly shifted into their lower energy configuration. That region would form a bubble of true vacuum surrounded by the false vacuum of our current universe, and then the bubble would expand. The boundary between these two states of reality would move outward at the speed of light. Everything inside the bubble would obey new laws of physics. The fundamental constants governing particles and forces could change. Atoms might not be able to exist in the same form. Chemistry might no longer function. Even the structure of matter itself could be completely different. Anything made under the old laws of physics would simply cease to exist. From the outside, this expanding bubble would be invisible until it arrived. Because it moves at the speed of light, no signal could travel ahead of it to warn anyone. One moment the universe would appear normal. The next moment the bubble would arrive, instantly rewriting the physical rules of reality. There would be no time to react, no time to observe it approaching, no time to escape. Every atom, every star, every galaxy would be transformed instantly. Fortunately, calculations suggest that if vacuum decay is possible, it is probably extremely unlikely. Estimates based on current measurements imply that the lifetime of our vacuum state could be vastly longer than the current age of the universe. But the unsettling truth remains: we cannot rule it out completely. In fact, modern measurements of the Higgs boson, discovered in 2012 at the Large Hadron Collider, place our universe in a curious position. When physicists analyse the properties of the Higgs field, the field responsible for giving particles mass, the results suggest that our universe sits right on the border between stability and instability. In other words, our vacuum may be just barely stable enough to survive, or just barely unstable enough to eventually collapse. Physicists continue studying this question intensely, but the answer remains uncertain. The universe may be perfectly stable and destined for a slow, quiet heat, death trillions of years in the future. Or it may exist in a delicate balance that could eventually tip. Yet despite these unsettling possibilities, there is something remarkable about the moment in cosmic history we inhabit. The universe is about 13.8 billion years old. For most of that time it was not suitable for life. Shortly after the Big Bang, it was too hot and chaotic for atoms to form. Later, stars and galaxies began to emerge, forging the heavy elements required for planets and biology. Eventually, somewhere on a small rocky world orbiting an ordinary star, life appeared. Billions of years later, that life evolved intelligence. Now that intelligence is capable of looking outward and understanding the universe around it, humanity exists during a narrow window in cosmic history. Before us, the universe was too young and violent. Long after us, the universe will be far colder and emptier. Right now, galaxies are still visible across enormous distances. Stars still burn brightly across the sky. The cosmic web still stretches across billions of light years. We live during the era when the universe is at its most complex. In the distant future, much of that complexity will disappear. Galaxies will drift beyond the cosmic horizon. Stars will fade, black holes will evaporate. The universe will slowly approach a state of silent equilibrium. But today, the cosmos is still alive with structure, light, and possibility. The vast emptiness of the universe may seem frightening, yet that emptiness also made our existence possible. Without the expansion of space, galaxies might never have formed. Without the delicate balance between gravity and cosmic expansion, stars might never have ignited. Without stars, the heavy elements that make up planets and living beings would never have existed. The universe may be dominated by emptiness, but within that emptiness, islands of complexity emerged: stars, planets, life and consciousness. For a brief moment in cosmic time, the universe is able to observe itself. And that moment is happening now. The void may eventually win. Dark energy may continue stretching the cosmos until galaxies vanish from view and the night sky grows silent. Yet the fact that we can witness this vast universe, that we can measure its age, understand its structure, and imagine its distant future, is one of the most extraordinary outcomes of cosmic history. The universe may be mostly empty, but within that emptiness something remarkable happened. It produced minds capable of asking why. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.